The sun is freaking big. How big is it?
You can fit 1.3 million Earths inside the sun.
I'm going to be a contrarian and say that the sun is really small because it takes 100 solar diameters to get from the sun to the Earth. You can fit 100 suns end to end between here and there.
And so that's why it takes 8 minutes for the light to get from the sun to the Earth, even traveling at 186,000 miles per second.
When it says big, it's relative to what,
right.
Captain?
Well, okay, so
Trek, yeah.
Like what about relative to the solar system in terms of mass?
Everything else is more or less trivial, except for Jupiter.
Yeah, it's like 99.8%, I think, of the solar system mass is the sun.
If the sun is that big, how come the little tiny moon can cover it up in an eclipse?
That's kind of a cosmic coincidence. The diameter of the moon is 400 times smaller than the diameter of the sun. But it turns out that the sun is 400 times further away from the Earth than the moon is from the Earth. So you have the size ratio and the distance ratio just about right, so that whenever the moon passes directly between us and the sun, it perfectly blocks out all of that light coming from the sun's center disk.
No, I'm no probabilistic scientist or nothing, but that sure seems like an odd coincidence to me. Are there any other places that we know of where you get total solar eclipses? Anywhere?
I mean, probably in the grand scheme of the universe or the galaxy, we would find such things, but not that I know of within our solar system for sure.
Earth doesn't deserve a moon that big and that far away.
Okay.
So if you compare the relative sizes of the moons of other planets, our moon relative to us is much bigger.
So if I got my super duper heat resistant suit, could I, in theory, stand on the surface of the sun? Is there a surface?
No to both, I would say.
You haven't seen my tailor.
I've always been a little foggy on this. Is there a transition from gas to then fluid plasma?
It's a transition in the opacity of the gas. There's no surface to stand on per se, but you can define what we call the photosphere, what we consider to be the surface of the sun. And that's where most of the light is coming from that we see of the sun. And that's the part of the sun that's really, really opaque. It's not as transparent as some other parts. And so that's sort of what we define as the surface.
What is a sunspot?
Sunspots are these intense regions, intense concentrations of magnetic field on the surface of the sun. And the presence of this magnetic field makes the surface a little bit cooler than the surrounding surface of the sun, just enough so it's not radiating as brightly as the rest of the surface of the sun around it. So it appears to us as a dark spot.
Why would a magnetic field cool the sun?
Intense magnetic fields have a special property in that they can inhibit the flow of heat. So it just means that region is a little bit cooler than the surrounding. It doesn't allow the material to convect.
What's a solar flare, by the way?
Solar flares can be associated with the activity that also creates sunspots. So you'll get these strong magnetic fields in those regions that Maria was talking about, where they build up a lot of energy that's stored in the magnetic field and the plasma that's associated with that magnetic field. And then something happens and that energy gets released all at once. And so it's a magnetic I sometimes refer to these as magnetic explosions, where you're releasing energy all at once. Almost none of the solar flares can you actually see in the visible spectrum. They are all in the X-ray spectrum, so it's an X-ray solar flare.
I have seen what looks like those kind of arc-shaped things that I assume were solar flares. Were those solar flares? They weren't?
Not yet, probably.
Yeah, right. So what you're describing is one of these arcades or trapped plasma along one of those strong magnetic field lines when that releases, and it happens very quickly, that'll disappear, and you might lose some of that out into space. But then the energetics of that are what create the solar flare.
Magnetic fields are kind of like rubber bands. If you stretch them too strongly, they can snap like a rubber band. There's a lot of energy stored in this thing. We sometimes refer to it as magnetic tension. Explosions equivalent to millions of hydrogen bombs going off at one time.
What would stretch a solar flare?
The surface of the sun is kind of wiggling around, it's moving around. Because we're talking about the convection on the surface. The sun also has little mini sunquakes that are constantly jostling around the surface. And so all of that.
You're not going to tell me that there's plate tectonics on the sun, are you?
No. But it's a similar technique. How you use seismology on the Earth to study Earth's interior. You use helioseismology to study the sun's interior, the different layers inside. All of that stuff means that these field lines store up a lot of energy and they just, at some point, can't take it anymore.
The plasma and the magnetic field together are the thing that's doing the stretching.
Is there a holy grail of solar physics? Like in neuroscience, they're all saying consciousness. If they can figure out the biological mechanisms of consciousness, that's it. That's the thing that everybody wants. That's how you get your Nobel Prize. How do you guys look to get you? What's going to get you your Nobel Prize?
For me, the holy grail is to truly understand the sun's dynamo. The dynamo is the process, the mechanism that generates the sun's magnetic fields in the first place. And if we can understand that, we can understand the sun's 11-year cycle of magnetic activity, that it repeats itself over and over and over again. And that's also related to the number of sunspots that we see on the surface every 11 years. And we'd also be able to then predict the sun in the future. And that's a very hard thing to do.
The other outstanding problem that is being explored by the Parker Solar Probe, which has done its first pass of the sun, is now out and going to loop around, getting ready to do its next pass next year, is what's referred to as the coronal heating problem. You've seen the corona of the sun, right, in the eclipse pictures, right? So
I was there in Missouri for the Great American Eclipse.
You saw
the corona. Yes, I saw the corona.
You saw the corona of the sun in your naked eyes.
That's
yes,
well, something like that.
Between the photosphere that Maria's been talking about, where the sun's atmosphere becomes transparent and is no longer blocking the light coming from the interior, but actually letting it out. And then the corona that you can see, there's what's called a transition region. You go from the surface of the sun at that photosphere being about 5,000 degrees Kelvin, 5,600 degrees Kelvin, but what's a few hundred degrees among friends, to 1,000,000 degrees Kelvin. And that's counterintuitive, right? You would expect as you got farther from the sun, it would get cooler. So there's some energy through some process around, and different people have different theories, but it has to do with something about what's going on in the magnetic field and this twisting and turning and knotting up and expanding and exploding, and we don't know why. So that's another outstanding problem. Whenever solar physicists don't know anything, they say, it's magnetic reconnection.
Yeah.
I always replace magnetic reconnection with magic.
Yeah.
How will the sun destroy us?
First, it will become a red giant.
That means it'll get bigger?
Yes. It finishes burning the fuel in its core in the way that it currently does now. And whenever it does that, it puffs up and it becomes so large, it becomes a red giant. And so large that it will engulf the orbits of Mercury and Venus. And the surface of the sun will get even closer to the Earth during the red giant phase. It's not clear whether the surface of the sun will get right up or even swallow the Earth, but it will certainly mean things will start to get really, really hot because the surface of the sun is getting closer to us.
What would you like our viewer to know? There's one thing you think we don't know that would be cool for us to know about the sun.
We were talking about solar flares. These solar flares, or coronal mass ejections, solar storms, send these clouds of magnetic field and charged particles to the Earth. that interacts with our Earth's upper atmosphere and our Earth's magnetic field, and it impacts astronauts in orbit, it impacts satellites in orbit, it even impacts our electrical power grid. So it's important for us to understand how the sun creates this magnetism in the first place so that we can try to predict it and be prepared when these things come our way.
I'm sorry, how does one prepare for a solar flare?
Well, you have people who their job is to watch the sun.
When Maria's talking about people, we're talking about NOAA. So there's a part of the weather forecasting arm is the space weather forecasting arm. So the Space Weather Prediction Center is a NOAA agency. They'll pick up the phone and start calling people, and they'll send out, emails and texts saying, hey, there's a solar flare coming. There's the potential for high energy particles. There's the potential for a geomagnetic storm. Take precautions in what you're doing, or don't do some of the things that might rely on, say, GPS, or bring on more generating power onto the power grid because we'll have to lower the load on the long distance electricity lines. So you need more local power to help. Satellite operators will, under certain circumstances, put their spacecraft in what's called safe mode. Right? Put it to sleep for a little while. When it passes, we'll wake it back up and it'll be all good.
I think this is so wonderful that here you got this most of the mass of the system, this gigantic flaming ball of hydrogen, and it sends out these huge flares, and there's still stuff that regular humans on Earth have some ability to protect ourselves from it, to protect our civilization from it. I mean, even though we're just a bunch of stupid apes. I find that immensely comforting.